7.1e, let's understand the relationship between sample size and variability of an estimator. Now, variability of a statistic, basically what it does is it just described by spread of the sampling distribution. So you can describe variability by looking at the spread, or that would be standard deviation, range, or IQR. Now, spread is determined by the size of the random variable. How big of a sample are you taking? Okay. As we saw in the previous slide, larger samples give smaller spread. So because it's looking more like the true population. Key thing here, spread of a sample distribution, by the way, does not depend on the size of the population. All you have to do, though, is be careful. You're going to notice written here in the black is if the population is greater than or equal to 10 times the sample. Remember this formula should look like the thing we did for the 10% condition. If the 10% condition is met, that the population is greater than or equal to 10 times the sample size, then it doesn't matter the size of the population we're picking from. As long as we have a large enough sample, we will be able to control more the variability of that statistic. Overall, though, larger samples do reduce the variability, but not necessarily the bias. You have to be very cautious. Again, are we having a biased or unbiased estimator? Go back to Chapter 4. Were there voluntary responses, convenient samples? If so, they're worthless. So you always have to keep Chapter 4 in the back of your mind. How was the sample taken? Does the sample itself and how it was taken create bias? So let's talk a little bit more about bias versus variability. So in these 4 different scenarios, the bullseye itself actually represents the true value of the population parameter. And then what we have are the various dots, are the various samples that were taken. So in sample D, what you're seeing here is there's no bias and there's very low variability. So they're considered low bias because the population parameter is the bullseye. These samples are hitting that population parameter. And you're going to see they're very close to each other, very low variability in that case. Now, let's deviate from that and let's go to sample B up here. Sample B, if you average out these samples, the average is going to hit close to the bullseye, so it means there's low bias. But this one has high variability. There's lots of spread. Remember, if we have to choose between a statistic, we want the one that is the least biased, true, but we want the one with the lower variability compared to the higher variability. Now, let's look at example C here. Example C, if we average these, it's going to be somewhere in here, which is going to be very high in bias, a very biased estimator, and it also has high variability, lots of spread. Whereas we wrap up with sample A, if we take the average of these, again, the mean is going to sit somewhere in here. So again, very high bias as an estimator, but there's very low variability in that case. Ideally, our ultimate goal to get to would be a scenario in D. Your next option, if D was not available, B would be the next best option because we do want low bias, but we want to try to minimize the variability as much as we can. This is an interesting real-life example. During World War II, the Allies captured several German tanks. Each tank had a serial number on it. Allied commanders wanted to know how many tanks the Germans actually had so they could allocate their forces appropriately. They sent the serial numbers of the captured tanks to a group of mathematicians in Washington, D.C., and asked them for an estimate of the total number of German tanks. Here's what they did. Here are 5 methods you could use based on those serial numbers. So for estimating the total number of tanks, which option is going to be best? The first option, they did this thing that they called a partition. And what it was is they took the maximum in value and they actually times it by the fraction 4/5. Okay, was that a good estimator? Or should they do estimator 2 that set the maximums equal to each other and look at that? Or should they do estimator 3 where they're going to take the mean and the median, so they add the mean and the median together and that's going to estimate it? Or number 4, they're going to take the quartiles, they're going to take quartile 1 and quartile 3 and look at that. Or should they do 2 times the IQR? One of these 5 methods actually gave them the best way to estimate how many tanks were really out there. So here we have the graph below shows the approximate sampling distribution for each of these statistics when they took a sample size of 4 from their population. So they were able to get information on 342 tanks, and they took a sample size of 4, created sampling distributions to see what it would look like. Now what you're seeing over here, this blue line actually represents the true population parameter, which was 342. So ultimately that was the correct answer. So as the mathematicians, before they even knew this, which one of these would have been the best estimator? So part A, which of these statistics appear to be biased estimators? So if you take a look at this, you would first want to go in, let's look at the twice the IQR. If you take all of these possible outcomes and you find their average, the mean on this is maybe going to be somewhere in here, which does deviate from the true one. The quartiles and the mean and the median, if you average out all of the dots on their sampling distribution, they're going to be pretty close to the true population. So these two in the green box are pretty accurate. Now the maximum, this graph is definitely skewed to the left, so we know if we take all these dots and average them out, it's going to be somewhere in here, which is very much far away. And then the partition method, if you take the average, it's going to be probably a little bit further or closer to the actual true population parameter than the maximum. If I had to pick 2 of these that are definitely going to be biased estimators, I think the first one that hopefully seems obvious to you all would be the maximum here. The maximum, the true average of all these is going to be way over here. So the maximum by far will be considered biased. There's one more in here I would consider biased. If we just go through the last 4 here and identify where the mean would be, I think we would say for these 2, they're going to be pretty close to the actual true population parameter. Twice the IQR is probably going to be about right here. The partition method, the mean is going to be pulled to the left a little bit, but a lot of the data is over here, so it's probably going to be pretty close to the true population parameter. So ultimately the 2 I would choose are the maximum and the twice the IQR as the biased estimators. Why? Because they are consistently too low. Their centers of true value are by far lower than the true population parameter. Now, which one of these 3 that are left would I consider to be the best unbiased estimator? These 2 right here, the mean, median, and the sum of the 2 quartiles are very similar. But notice the amount of variability in these 2 distributions as compared to that of the partition. Because of that, the winner in this case would definitely be the partition because it has the least amount of variability. So the partition method, even though it sounds kind of unique in how they're coming up with this, would have been the best estimator for them to use to determine how many tanks there truly were in the war. Now in part C, explain why a biased estimator might be preferred to an unbiased estimator. So keep in mind the biased estimators we said were these 2. Why might we prefer those over the mean, median, or the quartile method in this case? I think highlighting the maximum scenario here, again, we know the blue line is the true population answer, but look at all of the results for the maximum. Most of the results are actually close to it. So we might prefer the maximum in this case over something that is considered unbiased because it often produces estimates very close to the truth. Okay? Now, but what about why wouldn't we want to look at the mean and the median one? Well, the mean and the median one in this case is, yes, we would consider it more of an unbiased one as compared to the maximum, but there's a lot of variability in here, and that is not a good element to it. So in this case, the mean median is unbiased and quite a variable, but it's not close to the true value as often.